time to do the recap and challenge myself. So I wanted to. It's been a while, and maybe I don't know. Let's see how this goes. But I wanted to basically try to go through the basic textbook algorithms that I've been exploring on the channel. Yeah, basically, I wanted to take a look at that. So and see if I could now kind of, after all I've been working on. And that you see on the channels, if I could just easily understand them again. So let's see how that goes. I'm a bit afraid about this, but let's see. Let's see if I can understand them all quickly, sort of in a video. I don't know. I'll start with the deutsch-jozsa algorithm. So I can find an example quickly. Maybe this one. Just, I know there's a bunch of different examples out there. I just wanted to have like a quick look at a circuit and then see if I could just go through it. So, but that'll turn out to be more difficult than expected. Maybe some of those things. So what is this? Something simple. I don't want to spend too much time on this because that's kind of a pretty generic thing. I want a concrete example because that's sort of the oracle, right? Maybe I'll just go to my own video. Honestly, just pause the video at the circuit and then try to reason that. So, but I don't want to really. So quantum intuition YouTube. I don't want to really. Watch the video. The videos. No, that's
Hello.
That's Hello Quantum. Let me go to
So
my own
quantum
videos, playlists, the textbook algorithms. Here you go. So, Deutsch. So let's see. I'll just mute that because I guess you don't want to see my voice. Trying to find the algorithm, sort of the circuit. Okay, so here's a circuit example. So the so how do we start? What was even the problem that this was trying to solve? The deutsch-jozsa algorithm, I'll make the deutsch-jozsa algorithm was the first thing kind of solves from suppose that you're given a function, it takes 0 or 1 as the input and output 0 or 1. The function itself can be as common as needed. The algorithm is that it takes a bit as input. Okay. Was given two different inputs, x and y, checking the function f x is equal to f y. So what is the problem statement? Given a black box, the oracle, the function takes. We are promised that the function is either constant all zeros or 1 all outputs or balanced. Let's determine if f is constant or balanced. And here we've got a so look at that circuit as an example. Gives are used one is used on silicon. So that didn't work out as well I expected. I'm a bit lost. Black box can be solved efficiently by quantum computer. There's no error. So this is the box. Go here. I was supposed to understand this myself. Why am I even reading stuff? I mean, this is simply. So what is it doing? So it's a. So in this case, we have a control node in here. Or that that would be the equivalent. Wouldn't that be the equivalent of like a Hadamard and then a controlled Z, and the initial qubit is 1, right? And then another Hadamard, right? I think that's equivalent. So these equals to a control Z. So it's kind of a flag in this case. I kind of feel a bit lost right now. Just I think I jumped into it quite quickly. I done state is equal. Because that's kind of looking into the actual oracle. The oracle was supposed to actually be the function that's either constant or balanced, right? And so the quantum work which doesn't decohere X. First n bits are each in the state 0 and the final bit is 1. So to obtain the state is to maps the state xi to the state xi to the is either 0 or 1. So the function is either constant, so it outputs always zeros or always ones, or balanced, right? Was that the thing? Two null outputs or one null outputs, or balanced returns one for the half of the input domain and zero for the other half. The task then is to determine if f is constant or balanced by using the oracle. So the idea is you apply it in a superposition. But I'm not so sure what's the... So I'm not so sure. Okay, I think I got it, but it's because I kind of cheated and read these in here. I should have... So I should have... I mean, it's just the outcome we want, right? So it kind of makes sense. Evaluates to 1 if it's constant and to 0 if it's balanced. And I think the idea here is... the concept here is you're using that as a sort of a way to create a sort of a destructive interference in case the output is always constant or balanced, or in case the outcome is balanced. Destructive interference, exactly. But how does this really... Oh man, that was supposed to be the easiest one, and I just kind of got lost into the details, really. So this is really in this case, this is really the oracle in here. So this is the box, the thing that I've circled in here. And so in this case, it is a... in this case, this is a... No, sorry, the oracle is this here, not this. Right? The oracle is this. Because that basically means... Let me go to quirk. Quirk quickly. So So basically, this is initialized to 1. There's a Hadamard and then another Hadamard, and so if I would add another Hadamard here, and how is that control move the whole thing here? So zero zero 001. Oh, sorry, because here this is the sort of the latest sort of the. So basically creates that superposition that has a sort of, you could group that if that would be one register. I mean, the superposition you've got is basically the same thing with positive amplitude, and then with positive phase, and then this one with negative phase. If you consider that being the sort of the lowest value bit in this CAD representation here. And so and now is this a Control Z and Control X? More, and then we've got a 1 here. Because that's what we measure, yeah. 1. 1. Man, it's funny how these things is like, this is supposed to be the basic, but I'm just maybe lost into the definition of the problem itself. But this should be the oracle, which I mean, if I go back to the Wikipedia, which I don't know if I have been showing or not here, because I'm just again recording the tab. This is the Wikipedia page, and this is the way this is the schema looks like of the circuit. Maybe I was talking about this before, and I was not showing these again because I was recording the tab, not the screen. So this is when I said that I cheated, is because I was reading this part in here. Which is how do you read the answer of this, right? So let's put it this way. So I guess, I mean, the idea, let's try to reason that. So if let's say this function is constant, so it outputs all the time zeros or ones, right? Regardless of your input in here. Because of because of these, right? I see. So because there's a restriction here in how that's so there's an actual definition on what's the oracle doing, at least in, so this is the product. So now I think I get it. So basically, exactly. So basically, because here you've got that initialized to 1, that creates as a set now sort of the you've basically got like in if you take a look at the overall state, you've basically got the same the same input space twice, one with positive a phase and one with negative phase, because with these you're creating this negative uncertainty thing here, right? So, and if this is what the oracle is doing, and your function is constant, right? Then you're not gonna then you're not gonna destroy anything, because you, regardless of, but it leaves X untouched. So it's basically constant. So you're gonna have, this is really high level, but you're gonna have that. So intuitively, I'm having a hard time explaining it at that level, because what I had done in the video, I realized, is just go through one example, and it's a bit harder to kind of explain at the intuitive level what this is doing, just by taking a look at the box. But it's so the way my mind is going right now is that, because you've got, so if your fx, if the function is balanced, right? It means it outputs zeros half of the time, and one half of the time. Then you're getting 0 as an answer. How? Oh, it's embarrassing, really. That, what that literally means is that you've got, so if that is your whatever you've got here, your input, right? Because initially you've got a superposition with everything, right? So you've got, let's say, all the different possible input values in here. It's just that half of them have a positive phase, half of them have a negative phase. Right? It's kind of twice. It's just you have like ones are preceded with 0, these ones are preceded with a 1. So after you apply the oracle, basically, okay, so basically what the oracle will do is, it will leave it, okay, it would leave, now I get it, it would leave that, it would leave those, it would leave those unchanged. This is probably really confusing right now, but I'm going to try to explain it again if that makes sense mentally to me first. This is left unchanged, this part here, and then it transforms that first ancilla qubit. So basically, let's assume that the function speeds always. So let's assume the function is constant, right? So if the function is constant, it means it speeds 0 all the times or 1 all the time. So So this means that and we're now here. So this means in this case, if it's 0 all the time, 0 times 0 stays 0, right? If it's 1 all the time, 0 times 1 stays 0. So that stays 0 regardless. And in this case, so we're talking the case constant, yeah? So we're saying const, just so I don't forget, constant. And in this case, for those cases, so let's assume, so this is the case it's always outputs 0, this is the case it always outputs 1. In the case it always outputs 1, that's going to be a mess. That stays with 1. In the case that outputs 0, that stays 0. And and in that particular case, so we're talking about constant, right? But that's not, and because in that particular case, it should be destructive. And wait a second, then what we're doing then is we're applying that Hadamard in here. Because in this case, it's kind of destructive, and then so what you're going to measure is a 0, but that doesn't make any sense. No, yeah, sorry, we have to apply the Hadamard gate. The Hadamard gate, because now it's when the interference really happens. So in this case, we apply a Hadamard gate again, and because we know we initialized it at 0, right? That still should be. That still should be measuring 0. I don't understand why. Yeah, wait, but what do you measure? You measure that entire register here? That doesn't seem to match. Okay, the probability of measuring all zeros. So the probability you measure all zeros only if it's balanced, yeah? Because you're you're basically creating. I'm gonna get there. I realized I hadn't taken a look at this from that perspective, and so I think my video on the deutsch-jozsa algorithm is pretty stupid, the way that I did the first video, because that's harder to understand from that generic perspective, which is really about the actual constructive interference and destructive interference, which is the interesting part. So I'm happy that I'm revisiting this. Um, let me start from scratch. So what we're doing here, what it feels we're doing here, right, is we're kind of duplicating our input space, right? So this is what we're doing here by adding this one. So this is, remember, it can be n. It can be like, a larger amount of. So what we're trying to do is we're trying to build our algorithm in a way that it outputs 0 if the function fx is balanced. This means that it outputs. What was it here? Or balanced returns 1 for half of the input domain and 0 for the other half. So literally you've got like you've got your input space split into 2 portions. Sorry, I'm just gonna do this lower here. So into 2 portions, right? So those are all the portions that start with 0, and then they have all the other different combinations, and those are the ones that start with 1, have all the other different combinations. And because of the Hadamard gate in here, all the states have a minus, like a negative phase, and all those states have a positive phase. Having said that, what you're doing in here now is, so you're leaving the box is leaving this untouched, and it's applying the function here. As a product. So this means it's applying it for each of the first qubit on each of these elements here and here, right? Let's say, because the trick is in the places where we're going to switch that first from 1 to a 0, for example, then what you're gonna end up with when you interfere the results, when you kind of collapse that again, is that you're going to have that destructive interference. So if the function is balanced, this means it outputs zeros for half of the time and ones for half of the time. So this means for the same input, right? So this means that maybe I'm not interpreting that correctly. Oh no, that's addition, not product. Look, that's what I was missing. Okay, where this is addition modulo 2. Okay, so this is like addition. Okay, now it makes more sense. Now it makes more sense, because this means if it's balanced, right, it's going to output 0, 0, and 1 half the time. This means that for half of the elements in this bucket in here are going to still keep a 0 in front, and so this for half of these elements, and for half of these elements we're going to have a 1. And here actually it's going to happen the same, because the space of the input space is the same, it just has a 1 in the front. So you're going to have exactly the same zeros and ones, exactly, zeros and ones. Wait, am I doing this correctly? No, that's not what I meant. Sorry. Can I just remove this? Yes. So it's pretty neat. So basically, no. So this means that for half of this input in here. Wait. For half of this input here, we're gonna have a 0 and a 1. So this means, and we're only affecting that qubit. for each of the different, items in that space. So half of them will stay 0 and half of them will stay 1. We'll switch to 1 because it's 1 plus 0, 1. And here it's going to happen the same. So some of them will have a 0. So the ones that got a 0 in here will have a preceding 0. For some reason, it I'm a bit confused right now. For those where we have a 0 here, we're also gonna get a 0 in here, and in this case 0 plus 1 stays 1, correct? But then for those which are the 0, for those which we're getting a 1 here, we're gonna get a 1 here as well. But then for those inputs, but then 1 plus 1 is 0. But that essentially means that when we're now applying this Hadamard, wait a second. So let's imagine we had 0, that's our ancillary qubit, and then, I don't know, 0, 0, 1, and then you'll have on the other side of the packet, you have a 1, 0, 0, 1. So those are the ancillary qubits. Let's assume that this is we said a balanced, so a balanced, and let's assume that this gives, so this gives 0 for this input, and 0 for this input as well. So those things stay the same. Because 0 plus 0, 0, 0 plus 1, 1, so those things stay the same. So when you apply the Hadamard, it will just go back to to 0, because those things don't cancel out or something. That is what it's saying, I guess. Well, they do cancel out. No, they don't. Right? If it's constant, that's ridiculous. I mean, how can it how can it take me so long to figure that out? Uh, so in the case it is constant, I can take a look at this way. Can I take a look at this way? So in case it's constant, what happens? It's easy for me to see, maybe. So in case it's constant, this means this. Let's say this is always outputting 0, right? So if this is always outputting 0, then this is going to be 0 plus 0, and this is going to be 1 plus 0. So this basically stays as it is, right? And then when I would do a Hadamard just on those here, I would see a 0 value. Because it basically goes back to like nothing has changed. And if the function inputs 1, then I'm just flipping things around. So the same happens, because then it inputs always 1, then this will become 1, and then all the other possibilities, right? So this 0 becomes 1, and then this 1 becomes 0. So we just have the sort of the things like, it just flipped, right? You just flip the spaces. So basically, when you're gonna interfere those, it's the same. So it should go back to 0. This in the case it's constant. In the case it's balanced, why does this? In the case the function is balanced, it means for half of this is going to stay the same. So then let's assume, now I'm going to use the green, and let's say for half of my space is going to be 1, and for half of my space is going to be 0. And here on the other side, for half of the space, for the first half of the space, it's going to be 0, right? Is it? Yeah, because let's assume the first half of the input space, it outputs a 1, and for the second half it outputs a 0. So in this case, it's going to be like, you're going to have like these. And now, so now you've created kind of 4 spaces, or like you have those 4 buckets. And so and so they would cancel out, right? So I mean, here you would have, for example, the case ones and all zeros, and here you would have the case, you know, one and all zeros with a minus. So they would just cancel. I don't see how that is the other way around. What am I doing wrong? So we have the function implemented quantum order. The orca maps x, y to x, and see if you go for the else implementation, applying the quantum oracle. Don't want to take a look at this. I just want to sort of intuitively try to figure out. I feel I'm on the right track, but I'm missing something. I'm maybe interpreting something wrong. So I mean, they cancel out, and that's why you read a zero at the end. That's kind of, but then I'm reading wrong the balance, the constant side of things, where I should be getting a one. Okay, so here we're here doing these, and basically here, so because here you would have, let's say, the state 1 0 0 0, like let's assume n is 3, right? So you would have that thing would be in here as positive, but then but then you would have it as well on the other side as negative, right? So you've got, let's do it. Give me a second. Let's try to do something differently here. Let's try to make an example, a more concrete example. Let's say, so we've got, let's say n equals 2. So then you've got 0. This is your ancilla bit. 0, 0, 0, 1, 1, 0, 1, 1, right? And this is all zeros. So, because that's your ancilla qubit. And then you've got 1, 1, 1, 1, and then you've got the same thing here. 0, 1, 1. Now, if we assume that this is balanced, right? So these are your two different input spaces, the same one. And those, remember, they have a minus, right? So, and now if we assume it's balanced, it means for half of them it's 0, and for half of them it outputs 1. Let's assume that f of x it's like 0, 0, 1, 1, right? So it will be the same here, right? 0, 0, 1, 1, same input. This is the input. So then what this would evolve into is, because you're doing the plus in here, so you're going to have 0, 0, and here you're going to have 1, 1. So 0, 0, 0, 1, 1, 0, 1, 1. And then here you're going to have 1, 1, right? And then what did I just say? Oh yeah, and then 0, 0, because it's modulo 2, 0, 0, then 0, 0. 1, 0, 1, 1. But remember that those have a minus here. And now what happens is that if you do a Hadamard just on those, so now we said it's supposed to be balanced, right? So what they all get destroyed because you have, so regardless of the ancilla qubit, you've got like 0, 0, minus 0, 0, 0, 1, minus 0, 1, 1, 0, minus 1, 0, 1, 1, minus 1, 1. So it all gets cancelled, so you measure a 1 balance. And now let's do the same, assuming it's constant. So let's remove these two. Let's remove all these. So faster with my finger. So, and now let's assume that it's all zeros, right? So what you get in here now, if it's all zeros, then you've got 0, 0, 0, 1, 1, 0, 1, 1. You've got 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Huh. I think I'm doing something wrong with the Hadamard when I'm just doing a Hadamard on a portion of the subsystem. Doing something wrong in here. Or because remember that those things have minuses. So if I would do a Hadamard in here, so let's do an example. So if I would do a Hadamard of this, what would happen? That seems to maybe be key to kind of understand better this thing with the uncertainty stuff. So if I would apply a Hadamard in here, right? So and I'm going to write on that. So there's 0, 0, 0, and I apply a Hadamard to those two in here. So I'm basically getting like all the possible combinations, right? 1, 0, 1, 1. So this is what this kind of unfolds into. Now, what will happen in this case? So this is I've done this case and this case when I've already got a minus 1, 0, 0. What's wrong? What am I doing wrong? What am I doing wrong? What am I doing wrong? We apply the hammer mark only here. So that falls back into 0. 0 minus 1, 0, right? But I'm still measuring a 0 here, and that's not what this is saying. Whereas in the previous example, I was having a 1 here and a 1 here, and I was having a, because this was like that, and so I was having a 0 here and a 0 here, and in that case is maybe the interesting part, because now when I do a Hadamard, help. So when I do Hadamard on this, I'm doing this for an hour now, and I haven't really been able to figure out. I'm just so stupid. I feel so stupid. It's modulo 2. Or am I just doing this wrong all the time, and the ancilla qubit in this case is considered to be this one. So let's do a quick, maybe just taking a look at the whole thing from the wrong perspective. So let's do it again once more. If not, I'll just do another video on that as usual. So let's say we are 0, 0, 0, 1, 1, 0, 1, 1, and 0, 0, 0, 1, 1, 0, 1, 1, and here we've got the ancilla qubit. So here's going to be zeros, here's going to be ones. Wrong. Again, let's start from scratch. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1. We've got all the 8 possibilities. Let's say the ancilla qubit is the lower bit qubit. So this means that this is going to have a minus, this is going to have a minus, this is going to have a minus, this is going to have a minus. Exactly. And now let's say that, okay, and now let's say that let's say that the function is constant, so it outputs a 0 all the time. Okay, so remember n is 2, constant function. Good. So this means that we are going to add a, not constant, but balanced. And let's say that it's the following way. So this is the function, and if this is the input, it outputs 0 and 0, here outputs 1, here outputs 1. So this means that this thing turns into So this stays the same. Then this stays the same because it's balanced. Here stays the same, right? Because it's 0. So at 0, here stays the same with a minus, right? Right. Here, now we get a 1. For this. So in this case, this stays to 1, 0. 1, 1, 0, 0, minus, yeah. 1, 1, 1, and then basically minus 1, 1, 0. And so now, and this is, we said, is balanced. Now it makes sense, because now if we ignore for a second the ancilla qubit, we see that the leftovers are, there's always like there's destructive interference, 0, 0, minus 0, 0, 0, 1, minus 0, 1, etc. This now makes more sense. And what if it's constant? So what if it outputs always, let's say it outputs always 0. So then this is transformed into the same, basically. Minus 0, 0, 1. Yeah, see, but that's what doesn't make sense. Only I don't know. I'm just taking a look at it from the wrong perspective, maybe. Dobra, good. So I'll finish this video here. I'll do another one because it's just been too long. But I mean, I think it's just a matter of I'm getting lost somewhere in a stupid way. To sum up my current understanding of this is you're kind of duplicating your input space, and basically half of it is negative, has a negative phase. Yeah. And then by applying these, you're kind of you're kind of playing with the phases in a way that when you're gonna then do another Hadamard, it's gonna have full like destructive interference, and you're gonna read a 0 if it's balanced, or non-zero if it's constant. But I just can't. I maybe just making a mistake somewhere in my reasoning here. But I think that's kind of the overall idea. Let's see. Good. Great attempt. Got a stuck at the deutsch-jozsa algorithm. Yeah, but I think it's helpful to come back to these things. Perfect.